For the homework assignment on pages 434 and 435, I've chosen 3 problems to just give you some help with. And so this first problem, number 14, is an illustration of what we talked about in class today regarding translating a parent function. So what I want you to do is come up with a table of values for the parent, which I have identified for you here. And then we'll talk about how the H and the K numbers are going to be added or subtracted to these XY values to come up with the translated parent. And then we'll graph both of these on the same coordinate plane. So let's start by getting a table of values for our parent function. And we're going to use those same inputs that we used yesterday. So when x is 0, 1/3 of the 0 is 1. 1 times 9 is 9. When I let x be 1, of course that's 1/3 to the first, it's 1/3. And 9 times 1/3 is 3. When I let x be 2, 1/3 squared is 1/9. And 9 times 1/9 is 1. Okay, now we'll do the negatives. If I let x be -1, 1/3 to the -1 is 3. 3 times 9 is 27. And then if I let x be -2, 1/3 to the -2 is 9, and then 9 times 9 is 81. Okay, so this table represents the ordered pairs, at least 5 of them, for the parent function. Okay, well now let's look at what the translated parent table of values looks like. I notice that I'm adding 7, which means that the H value actually that represents horizontal movement is -7. Remember, you really, when it comes to horizontal movement, you really have to think opposite of what it looks like. We're actually going to be moving left 7 places. And this other number that we call K represents vertical movement, and it's -3. And so K, of course, representing vertical movement, so this indicates that we're going to be shifting down 3 places. So the translated parent function table is going to be made up by doing this. I'm going to take -7, and basically the -7 means I'm going to be subtracting 7 because I'm moving left 7 places. So I'm going to subtract 7 from each of the x coordinates. So 0 minus 7, 1 minus 7, 2 minus 7, -1 minus 7, and -2 minus 7. Okay, and since I'm moving down 3, that's like subtracting 3 from all of the y coordinates. So 9 minus 3, 3 minus 3, 1 minus 3, 27 minus 3, and 81 minus 3. Okay, so we're going to go to our next slide where I have a graph, and we're actually going to plot these points on the same coordinate plane. Okay, so I'm just going to make a quick list of these points. And we'll start with the parent function, and I'll do that in blue so we can keep that straight. All right, so I notice that I've got to be able to get all the way up to a y value of 81. And so that's going to require changing my units a little bit. So I think I'm just going to do units of 5. Okay, I should have plenty of space if I do the y units in 5s. And once again, you may choose to do something different, and that's okay. So the point 0,9, let's see, I'm going to do the parent in blue. Change color. 0,9 would be about right there, just below the red line. 1,3, so I go over 1 and then about halfway. 2, 1, a little closer to the x-axis, and then negative 1, 27, 5, 10, 15, 20, 25, and then just a little higher. And then negative 2, 81. And I've got, this gets me, I think I've got 15 squares, so that would be 75. I'm just going to go up a little bit higher. Okay, and draw my curve. All right, so if all you need is just a little bit of space to get that final point, then you don't need to worry too much about that. That's okay. So we have typical exponential decay. Our B value is between 0 and 1. Okay, so now on that same graph in red, we're going to show the translated parent. So let me get these points. And we'll plot them in red. So we got negative 7, negative 6, or positive 6, sorry. So that's just a little bit above. Negative 6, 0. Negative 5, negative 2, which is just a little bit below. Remember, this blue line is negative 5. Negative 8, positive 24, 5, 10, 15, 20. The blue line would be 25, so I'm going to go just below. And then negative 9, and then we're up to 78. Well, remember, this top line is 75, and I'm just going to go a little bit more to show 78. So the red is a shift of that parent function 7 places left and 3 places down. So you got to keep in mind, we talked about this in class, the blue curve, the parent, had a horizontal asymptote of the x-axis. Well, if we shift this whole graph down 3 places, that means that I've got a new horizontal asymptote. And remember, the units have changed, so I've moved that horizontal asymptote down 3 places, and it's hard to draw a straight line like this, but this line is y equals negative 3. So basically, I should be always approaching this new horizontal asymptote, y equals negative 3, because my entire graph shifted down 3 places. Okay, so the blue, you don't have to show the horizontal asymptote for the parent, but I do want you to show it, and you can kind of guesstimate where you think negative 3 is. I should be illustrating that I'm approaching this forever, going toward the positive infinity. All right, so that's what you're going to have, the 2 tables and the 2 graphs, and that takes care of number 14. Okay, I thought I'd also help you out with number 25. The book wants you to take the $400 investment at this interest rate for this amount of time, and what would that result in if we did continuous compounding? Well, remember, I showed you in class today, we have a formula whenever we want to calculate interest that is compounded continuously, we will use this formula. Okay, so our principal investment amount is 400. So you're using your calculator, you'll do times, and this is where you're going to use that e to the x button, e to the the power for e will be 7.6 in decimal form. So that's 0.076 times the number of years, which will be 1.5. Okay, so in your calculator, in parentheses, the exponent for e should be 0.076, the decimal form of 7.6%, times 1.5, which is t, number of years. All right, and so we always round these interest problems to the nearest penny, and so you should get $448.30 for the continuous compounding. Well, I ask you to do something extra, and that is take these same numbers, but instead of doing continuous compounding, what would it look like with semi-annual compounding? So for this more traditional way of compounding, we're going to rely on this formula. All right, so our total amount will be same investment, $400, 1 plus the rate, again, in decimal form, 0.076. N for semi-annual compounding, that means twice in a year, so N is 2. And then the exponent will be N again, 2 times 1.5. So 2 times 1.5 is 3. All right, so you're ready to get your calculator, and let's see what we come up with. So 400, and then you can use your left parenthesis, 1 plus 0.076 divided by 2, close your parentheses, raise that to the third power, and you should get, rounded to the nearest penny, $447.35. And this is typical. We should expect that our continuous compounding amount should be a little bit more. How much more will depend on the number of years, the interest rate, but especially the number of years that we're compounding. So it is a little bit more, and I just wanted you to see in certain cases the comparison between continuous compounding versus a more traditional way of compounding. Okay, I thought I'd help you out with this number 30 because it's a little different than what we looked at in class. We have this student that wants to save $8,000. So in other words, he wants his final amount, investment amount, to be $8,000 in 5 years. He's earning 5.2% interest compounded continuously. So I see, whenever I see compounded continuously, I know I'm using this formula. Well, the thing that makes this a little bit different is we're given the final amount after interest is earned. In other words, we're told what A is, and it's going to be our job to find out what P is. All right, we know what the rate is, 5.2% in decimal form, and we know how many years. So our exponent for E is going to be 0.052 times 5. Okay. So grab your calculator and find out, just do e to the power. Just find your e to the x, and in that exponent, in the parentheses, you're going to put 0.052 times 5. Close your parentheses, hit enter, and you should get 1.296. I would not round this, I just leave it in your calculator or write it down. 1.296930087. I always like to wait until the final step to do rounding, and that gets us a little bit more precise. Okay, well, a more proper way of writing this, I guess, would to let this be the coefficient, and we'll put P on the end of that. Doesn't really matter, but it looks better. Okay, so do you see what happened? We're solving basically for P. So we went ahead and evaluated in our calculator. We found this number, e raised to this power, and we got this long decimal. Well, you can probably see now how we're going to solve for P. we're going to divide both sides by this long decimal. So in your calculator, you're going to do 8,000 divided by that decimal, 1.296930087, and you end up with a final answer rounded to the nearest penny of $6,168.41. So the amount needed to be invested at this rate for that amount of time with continuous compounding to get to 8,000 would be this amount, 616841. Okay, well, I hope that helps, and I hope now you'll be able to do the other problems. So just contact me if you have any questions, and I'll see you tomorrow.